Hello, welcome you all. So the second video for the day, this is the JEE main chapter-wise test on electronic devices, semiconductors. These also have questions of communication, so I have added communication also in the title. Now, as per my analysis, 16 are easy, 11 are of medium difficulty and 3 are tough. I think 1 and 2 questions are beyond the usual syllabus that is being required. So 84 plus would be a good score and 104 plus is going to be a very good score as per me in this particular paper. Now, this is today I am celebrating an year, almost 365 days before I started this video making using those NTA Abhyas tests, and here also I am today uploading a video on NTA Abhyas chapter-wise test. So it was really a remarkable journey for me. It has helped me a lot as a teacher, as a person, and thanks everyone for being a part of the family of this Helping Hand channel. So let's begin. Question number 1. The IV characteristics of an LED is. Now this is a very good question. This is even asked in CBSE exam, though not given in NCERT. It is given as the additional material for the NCERT supplementary material, you can say. And you all know that for the LED the curve is this one. This is with different colors the IV curve varies, and you can make it out that for same current the voltage needed for blue light would be greater than that needed for the red light, and in the same sequence you can have, or you can say for same voltage we will have more current in the case of red as compared to the blue one. So this is a very standard question that you should all be remembering. Such questions have already been asked in the examinations. Second, in an NPN transistor is common emitter amplifier, 10 to the power 10 electrons enter the emitter in 10 to the power minus 6 seconds. If 2% of the electrons are lost in the base, then calculate the current transfer ratio and the current amplification factor. So here it is basically alpha and this is basically beta. So 2% of the electrons are lost in base, that means IB is equal to 2% of what we say is IE, because all the current start from the emitter. So this is IE, so therefore IC would be 0.98 times IE. So what is alpha? You know alpha is equal to IC over IE, so that comes out as 0.98, and the beta you write it as IC over IB. And IC over IB, if you will do, you just divide both these two equations, IC by IB, it would be 0.98 over 0.02, so it comes out as 49. So option B would be the answer. You can directly take it in that particular way. Okay, next we move on. The next is question number 3. An NPN transistor in common emitter mode is used as a simple voltage amplifier with a collector current of 4 milliampere. Okay, so just write it down. IC is 4 milliamperes. The positive terminal of a 8 volt battery is connected to the collector through a load resistance RL and to the base. Okay, so the same battery connects to the collector as well as to the base. One is RL, one is RB. VC is 4, VB is 0.6 and beta is 100. Calculate the value of RL and RB. So this is NPN. So NPN means it would be something like this P2N. So we can draw it like this. So with the help of RL, it is connected for collector by this voltage. You can say this is 8 volt battery here. This is like this, and this would be the grounded one which usually show. And to the base, it is connected with the help of this RB, this battery. So it would be something like this. This is RB and this is RL. Okay, so this is what we are given. So this voltage VCE, this is given as 4 volts, and VBE, this switch VBE. So VB minus VE, you can say VBE is equal to 0.6 volts, and beta is 100. Beta you know is IC over IB. So IC over IB is 100. That is also given. Now you have to find the value of RL and RB. So looking at it, just apply this loop law in this loop. What you will have, VCC, which is 8 volt, minus this current would be IC, minus IC into RL minus VCE will be 0. Loop is completed. So what we are getting, VCE is given 4, so 8 minus 4, 4 is equal to IC into RL. So IC is given, so RL would be 4 upon IC. IC is 4 milliampere, so put 10 to the power 3 over here. So what we are getting it, is 10 to the power 3 ohms. So the load resistance is 1 kilo ohm, so we are left with C and D option. Now RB. For RB, take this loop, let's say this one, this loop. So for this loop, what we have, 8 minus this current would be IB flowing in the base, minus IB RB minus VBE equal to 0, and VB is 0.6. So IB RB comes out to be 7.4, and what is IB now? You can make it out. IB is IC by 100. IC by 100 means 4 milliampere over 100 into RB, that is 7.4. So the value of RB, you can make it out as 7.4 into this become 10 to the power 5 by 4. So it would be very high usually not that high, but it is given. So 4 upon 7.4, it would be 1.34, that is 1.85 into 10 to the power 5 ohms. So D option would be there. That would be the answer here. Usually we don't have like this, but this is the data here. Next, the maximum frequency for reflection of a sky wave for a certain layer of the ionosphere is found to be f max is 9 root n. That is a standard result. You know 5 max is 9 root n max. N is the density, whatever is given, that usually I tell you, and you must have seen in the revision video for communication. If you have not seen, please see it. On a certain day, it is observed that signals of frequency 8 megahertz are not received by reflection from the f2 layer. So this f max is 8 megahertz. So you have to calculate this n max. So the value of this n max comes out to be 8 square, 64 into 10 to the power 12 over 81. So 64 over 81, if I will do, it would be something slightly less than 0.8. So it would be 0.79 into 10 to the power 12. So going by the option, it would be option A. That would be the correct option. Next, the forbidden gap in germanium is 0.72 eV. Given Hc is 12400 electron volt angstroms. Okay. The maximum wavelength of radiation that will generate electron hole pair. So simply energy is Hc by lambda. So 12400 eV angstrom over lambda, let's say written in angstrom, would be equal to 0.72 eV. So this lambda will be in angstrom. What we will have, this would be, what you can say, lambda would be 12400 divided by 0.72. So definitely greater than 12,400. So it would be, but not like this much. It would be the option C. That is the closest one I can directly see just by checking the order of the magnitude. Next one. In a current, in a common emitter, configuration of a transistor, base current is given, beta is given, then the value of IC is. So what I feel, beta typically common emitter. In a common emitter configuration, usually this should not be the beta. Beta is typically not 0.9. I don't want to agree with it, but the options here are all in microamperes. Usually what we have, IB in microamperes and ICI in milliamperes. So here just they have made a question, so do it like that. Usually in such cases, it's better to write it as IC by IE, but here the values are all of the same order, so there is no point in going for a higher value. So what we will have, IC by IB, and this is given as 0.9. So the value of IC is 2 into 0.9, that is 1.8 microamperes, and this is, I think, a very unusual for a transistor to have IC lesser than IB, but we are left with no other choice. I don't think it's a very nicely designed question. Someone has just designed it. In a common emitter transistor amplifier, the output resistance, you usually call it RC or RL, is 500 kilo ohms. Current gain is 49. If the power gain is this, the input resistance is what we say the power gain. The power gain basically is what we say voltage gain into current gain. So you write it as V out over V in into AI. AI was you write as, this is beta. So V out by V in AV you would usually write as beta RC by RB, or R input, whatever you write, into beta. So it was beta square RC by RI, that you directly remember, I suppose. So this is 5 in 10 to the power 6. So RI would be beta square 49 and 49. RC is 500 kilo ohms and 5 in 10 to the power 6. So now you can do it. This is almost 50 will go, and this is 50, that closer to 250 it would be, and it would be 240 kilo ohms if you calculate it completely, not kilo ohms, sorry, it would be of the order of ohms. Okay, so standard application of the basic formula. Next, transistor is used as an amplifier in common base mode. Okay, so here it is common base mode, usually not asked as such in your CBSE course, but somehow some questions have been asked in the examination, so we'll attempt it. With a load resistance of 5 kilo ohms, the current gain is 0.98, the input resistance is this, what would be the voltage gain. So again you will have voltage gain as current gain into R output upon R input. So 5 kilo ohms, that is 5000 over what we have 70. So it would be basically 70 also, 70 into 0.98, it would be closer to 70 only. So this would be 70 if you solve. So go by option A in this case. So you always remember, we use CE mode because CE mode gives both the current and the voltage gain. Here what you are seeing, voltage gain is there, but the current gain is not there. An amplifier has a voltage gain AV is equal to 1000, the voltage gain in dB. Usually this is not a part of your syllabus. I don't know why they have asked. Just for your knowledge, the voltage gain when written in dB, this is the gain in dB. Usually what we write it as, this gain is written as 20 log, basically the voltage gain that you have output upon input, that is 1000. So it would be 20 log 1000, and log 1000 you know is 3, so that would be 60 dB. That would be the answer here. So I don't think it's better to leave it. It's not in your syllabus as such. How many NAND gates are required to form an NAND gate? You know what we have for a NAND gate. Usually a NAND gate, this is a NAND gate. Now invert the output, so invert the output, feed that both as a part of the another NAND gate, and this would be an AND gate. So the minimum number is 2. You can't have in 1, you can have minimum in 2. An N-type semiconductor has a large number of electrons, but it is electrically neutral. Yes, that is, if N and P both are neutral. N-type semiconductor is obtained by doping an intrinsic semiconductor with a pentavalent 5th group impurity. Yes, so both are true, but it is not an explanation. The explanation is like that: you have not removed electron or protons. The number of electrons and protons are going to remain the same. So we will go for this one. Both are true, but that is not a correct explanation. Next. A 5 kHz frequency signal is amplitude modulated on a carrier wave of frequency 2 MHz. So this is FC and this is F of message. The frequency of the resulting signal, we know there are 3 frequency: FC, FC minus FM and FC plus FM. So FC is 2000 kHz, that's okay, and 2000 plus 5, that would be 2005 and 1995. So that is the correct option. The 3 frequencies will be like this, so go for option D. This is all covered in that particular revision video, you can check it out. A 2-volt battery is connected across AB as shown in the figure. The value of the current supplied by the battery when in first case positive terminal is to A, so like this. So in this case what you have, D2 won't conduct, D1 will conduct. So in this case the effective resistance is 5 ohms, so the current in the first case would be this 2 by 5, that is 0.4 amperes in the first case. So we are left with only one option, but let me try again. And when you have connection like this, B is to the higher, then D2 works, D1 won't work, so you will have 10 ohms, so it would be 2 by 10. So I2 would be 0.2 amperes and this would be 0.4 amperes. Basic question, many questions have been asked. If the diode is forward biased, treat it as a wire. If it is reverse biased, treat it as a broken wire or an open circuit. So this is the option D that I am going to pick here. Next one. To get an output 1 from the circuit shown in figure, the input must be, so final gate is AND gate. So for AND you need both 1. So C has to be 1. You are left with only one option. So that would be the case. So here if I do 1 and 0, it would be 1. So 1 and 1, it will give me 1. So that is an easy one. The options are not very good design, and I think such questions were there in the full test last year. I solved many questions, I think, are there from the same test. In the circuit shown, the diode will conduct current, so it should be forward bias. This is 4, so it should be greater than 4 volts positive side. So it would be not complete cycle, not complete positive. It will only when it is greater than 4. So option C is the most appropriate that you can take it here. Next one. Two identical capacitors of capacitance C each are charged to the same potential V connected to the two circuits at t equal to 0. At t equal to 0, charge on the capacitor at time t equal to RC, we usually denote it as t equals to tau. So now, in the first one, just look at it plus minus. So this is forward bias, so here it will discharge. Here it is reverse bias, so it won't discharge. So for this one, the charge will remain same CV. So we are left with 2 options, and for this one it will reduce, and in one time constant unit becomes 1 by E. So that's options are quite easy. So go for option 2. I think this is also a repeated one from those tests. Now the frequencies in the UHF, UHF frequencies are much greater. They are much greater than that 30 megahertz. So they are propagated by the space wave propagation, not the sky wave, and ground wave is definitely not going to be the choice for them. Next one. The maximum distance between the transmitting and the receiving TV towers is capital D. If the heights of both transmitting and receiving towers are doubled, then the maximum distance is, that D is equal to root 2 RHT plus root 2 RHR. That is the formula that we use. Now what it's saying, both towers are doubled, so this factor and this factor both will get root 2 times, so overall this factor will become root 2 times D if you do this, if both are doubled. So go for option B. Both the things A plus B, A and B both are becomes root 2 times, so the sum will also become root 2 times. You can do, don't take 2 times, it would be root 2 times. An AM wave is given by, this is a standard expression what we usually write. We write it as AC into 1 plus AM sine omega nt usually into sine of omega ct. That is the way we usually write like this. This is what we have, AC 1 plus AM or 1 plus mu, sorry, not AM, 1 plus mu, that you usually write AM by AC. That is the better thing you have. Mu you usually write A sine omega mt. So comparing it, this is the message frequency, this is the carrier frequency. So the modulating, that means the message frequency Fm would be omega m by 2 pi. So what is omega m? This is 12560 divided by 2 pi. So what we are left with, 2 pi is 6 point something, so it would be 200 something, to 200, or what we can say 6 point something, so it would be 20 times, so it would be 2 kilohertz. Go for option A. As per this options, it would be 2000 hertz. So go like this. Next one, the amplitude modulated current, again the same thing what you have, the same style you will have. So this one is what you can say AC. So this is of the carrier. So the RMS value of carrier current, so this is mu, this is AM by AC. So this is the AC, this is the peak value. So the peak value of carrier is given as 125. So RMS you know would be 125 by root 2. So what is the option? Option A is the option. Go for it. That would be the answer. Next one, 1% of 10 to the power 12 hertz of a satellite link was used for telephone. This is a very common question. So 1% of the 10 to the power 12 hertz, that means the total bandwidth that you have available is 1% of 10 to the power 12, that is 10 to the power 10 hertz. The number of channels or subscribers each requires 8 kilohertz. So number of channels would be, total space is 10 to the power 10, each requires a space of 8 into 10 to the power 3. So going by this would be 10 into 10 to the power 6. I write it like this upon 8. So it would be 1.25 into 10 to the power 6 number of channels that you can accommodate in this particular spacing. So go for option B. Next. Now a 1 kilowatt carrier is modulated to a depth of 80%, the total power. Again, usually this is not treated, I think this is generally not asked in our syllabus, but if you want to remember it, the total power is the carrier power into 1 plus mu square by 2. That is basically the power contained in the carrier plus in two sidebands, upper and lower sideband. So on detailed analysis, this particular results come. So here mu is 80% or 0.8. So this is 1 kilowatt. It would be 1 plus 0.8 square by 2. So that would be 1.32 kilowatt. But I doubt if you remember this formula, because usually it is not as such taught. So I think this is just one off question, and you just can remember if you want this particular result. Next, in a CE transistor amplifier, the audio signal means that is the modulating one, you can say, collected across the collector resistance of 2 kilo ohm is 2 volt. So what you have, this is a collector resistance, that means the output voltage is 2 volt. If the base resistance is 1 kilo ohm and the current amplification of the transistor is 100, the input signal voltage is, so what we have, AV is equal to V out over V in, and that is equal to beta RC by RB. That is what you usually write. So this is 2, this is V input, beta is 100 and RC is 2 kilo ohm, that is 2000, RB is 1 kilo ohm, that is 1000. So this is 200, so V in will become 2 over 200. So it is 1 over 100 volts. So you can write it as 10 millivolt, I think. So that would be the answer. So the answer would be option B in this case. The standard question for you. Such questions are usually asked. The circuit is equivalent to, now there is a thing called the De Morgan's theorem, or that Boolean expression you can do, but I usually tell students to just do by 0 0 0 one thing. So just these are the input, this is the output, try 0 0. So if I try 0 0, this becomes 1, this becomes 0, so this will become 0 because this is an AND gate, this is an OR gate, this would be 0, so this would be 0. So 0 0 is 0, that means definitely it is not a NOT or a NAND gate. Now you are left with OR and AND, so better try with 0 and 1 you can do from here. So this is 0 and 1, so 1 and 1 AND gate will give you 1 and 0 and 1 will give you 1. So let me repeat it for you for the second time if you got lost. 0 and 1, so it would be 1, and this 0 will, this is an inverter NOT gate, so it becomes 1 and 1 AND gate will give you 1, and 1 0 the OR gate will give you 1. So 0 1 is 1, so that means this is an OR gate, not an AND gate, because for an AND gate 1 will only come when both are 1. Next, the given electrical network is equivalent to, now just look at this, this is a NOT gate and this is a NOR gate, both input same, so it is also a NOT. So NOT of NOT, that means both nullify, it has no meaning, so this would be the answer. Which gate it is the NOR gate, so answer would be a NOR gate. Nothing to do, simply you can do just by observation. Always remember the NOR and the NAND, if both input are fed same, it acts as an inverter or a simple NOT gate. In a common base mode, the collector current is given. For an emitter current, the value of base current is, so beta you write it as IC over IB. So IC is 5.488 and IB would be IE minus IC, that is 5.60 minus 5.488. Always remember IE is IB plus IC, that is a fundamental equation for any transistor. So what you have, 5.488, this would be 2, this would be 9 and 8 1, this would be 1, so 0.112. So now what we are left with, it would be approximately, what we can say, okay, the options are really close. You have to be very careful. So now do the calculation. So let me write it as 5488 over 112. So let's try by 4. The easiest thing I can think of, it would be 28, and this would be 1, 14 is 3, 28 is 7, 2. Again do this 14, this would be 6, this would be again 8, and this would be 6. Again I can do by 2. Okay, so 3, 4, 3 and 7, and it is again okay, so it would be 49, because 7 cube is 343, so this is 49. So a perfect answer we are getting. Next one. In an NPN transistor amplifier, the collector current is 9. IC is given 90% of the electron diameter reach the collector. That means alpha is 0.9. So alpha is 0.9, then beta would be what we have, alpha upon 1 minus alpha, that is 0.9 upon 0.1, that is 9. So go for option A directly, I can say. Next one. Would there be an advantage of adding n-type or p-type impurities to copper? Why would you add to copper? Copper itself is a very good conductor, and for metals, if you add impurities, it basically increases their resistivity. It won't help. So it won't help. There won't be any advantage. You can directly say copper won't get any benefit of that thing. In the 3 parts of a transistor, emitter is off. Now this is the easiest one for you. No, it is maximum doped and of moderate size. Last one, for a collector, a common emitter configuration alpha and beta. I just told you. Beta is alpha over 1 minus alpha, and alpha is beta over 1 plus beta. So just look at the options. The first one is the appropriate one. So I think it was quite an easy one. Thanks for watching.